start streaming. Smaller group today. Oh, it would help if we're connected, right? So spent a decent amount of time looking at like angular momentum, defining it, all of that. And it seems like it's been kind of a slog, at least based on facial expressions that have been happening throughout the process, like defining things and all of that. Before we like really beat this thing to death, I just wanted to show one last little thing. So like we drew the free body diagram, and one of the first things I was saying is like that it's not, that the sum of the moments is not equal to 0 because it's equal to R of P slash O cross Fs, like that vector Fs, which is going to be that V0T along E1 plus R ER crossed with like a negative KR along that ER. So kind of taking that force vector, look at it as a force vector. All the ER cross ER terms, they all drop. That one drops out, like that cross product is 0. But then I end up with like a negative K V0T in that K direction. So my moment is a function of time. So no matter, times R. So unless R is always 0, it's got to be some function of time. That was the one thing that I wanted to like wrap up this problem with. That we can't have sum of the moments equal 0 and conservation angular momentum because that momentum keeps changing as we're moving away from the origin, from that point O. That was the last thing that I wanted to show. What's some of the highlights as we look back on all the great work that we did here? If sum of the moments is 0, angular momentum is constant. So there's like highlight number 1. Another highlight was that when we found that angular momentum around HO prime, let's go down here, or wait, where did we find it? Yeah, over here. Another highlight, when we define angular momentum in this rotational coordinate system, it's always this value, radius squared times theta dot in the mass. Like however big it is, however far, the bigger, so the more mass you have, the farther away you are, and the more you're rotating around your reference frame, like in that reference frame, the more angular momentum you have, at least for a point mass. But roughly the same thing for like rigid bodies rotating and stuff. So those are the highlights of this, all that hard work that you did last class and started, I guess, this whole week. It's been like angular momentum.
Can you show me the last one again?
I think that one we started one of the suggestions at the end of last class was like, hey, we could calculate angular momentum around O. And then we started to do that and ran out of time. So if you can finish that up, but what you'll find is that you'll end up with some kind of like function of time term there as well. So you could solve. You can either do either side of that equation. Since some of the moments is change in angular momentum, if you solve for moment and show that it's not zero, then you know that angular momentum is not conserved. It's not like constant. So either way. Not impressed. This was a lot of work. You put a lot of work into this. This is gold. Gold. Do you want? Yeah, go ahead.
So, like, we started doing it by doing like the angular momentum, but then like ended up just doing the other moments. Like, how would we like put that into an answer kind of?
So like we could write out here. So E1 and E1. ME0T R dot E1 cross ER, it's going to be sine theta in that K, and then plus ME0T E1 R theta dot E1 E theta is going to be cosine theta K. And then we have our normal like m r squared theta dot in that K direction, and then also another term er cross E1 mr v0 in this one's a negative sine theta. Okay.
Because we can start to see that we knew that the sum of the angular momentums was not zero.
Yeah.
Could we not have just written because we know this, do we have to do the math to find the angular momentum at zero? Or can we just say because we know it from C, we know that it's not zero?
That one, so part E, like if it's just asking like is angular momentum conserved around O, you can say no, it's not, because moment is not zero around O. Yeah. And yeah, writing out this full like angular momentum around O equation doesn't give us like a ton of new information, but the one thing that it does tell you is that again you have this like d0t in both of these, so there's going to be some function of time, which means that it can't, since time is an independent variable, there's no way that you could say like it's a constant. Yeah, so even if you do write this whole thing out, you still end up with the thing that, oh, it's got to keep going up. Unless you have the boring case that like r dot and r theta dot are both zero, but then the thing's just being boring, sitting at the origin. Yeah, should we do something? Do you remember last year, the Francis Scott Key Bridge? It was like a full-on disaster. Do you remember what happened? Or did you see those videos? What happened? A boat hit it, right?
In Baltimore?
In Baltimore, yeah. Yeah, this bridge in Baltimore. Luckily, I think for the most part, like they were able to get everybody off the bridge, but it caused like a lot of damage.
Yeah, the only people who died were on the boat, right?
Like yeah, maybe one person ended up dying that was on the boat. Does it show the collapse? Yeah. No, driving on it.
6 construction workers on the bridge.
But it would like when this happened last year, like a lot of news articles were saying like, oh, shouldn't there have been safety precautions? Like, shouldn't these engineers have been able to prevent this kind of disaster? But it, like with a boat this size, it's so hard to get it to move, either to stop it or even just change its direction. So there's like two versions of this question of like, all right, let's say you knew this was going to happen and you send a tugboat out. What does a tugboat need to do to stop this thing? So how long can it apply a thrust? Like if you have 1 minute before it's going to hit the bridge, how much thrust do you need? The other one would be like, because this, I think this was kind of this, imagine that there are like big rubber bumpers. How big of a rubber bumper do you need to stop a boat of this size? So these are two questions that we can get like back of the envelope calculations for. Like, is it even feasible to do this kind of work? So that's what I thought that would be a nice place to take off for today. Like, wrap up here for the week. Unless there's been like a new big like engineering disaster. Has anything else happened lately that's like terrible like engineering, like maybe engineering could have fixed it? The election, can't really do much about it. I don't, at least as engineers, I don't know how much we could have done about it. All right. So think about like stopping this boat. First off, like, do you know how big these boats are?
In meters per second.
In meters per second?
Yeah.
What is the speed right now? Does it tell us? Oh, 8 miles an hour. So V equals 8 mile per hour, which, and I think it's like 2.2, 2.1. 3.58?
As for the actual value.
Oh, the actual value. What'd you? 2.23 miles per hour. Yeah, like roughly a factor of 2. If you're moving 1 meter per second, you're doing 2 miles an hour. About. So that's our speed. And that's about how fast it was moving. Not very fast. Like if you were running fast, you could have caught up with it if you could run on the water, or if you were like running next to it. So first question is, like, let's say you send a tugboat out there and it's going to apply thrust. How do we set that one up? We want to know how long to apply thrust, an average thrust to this thing to bring it to a stop.
Do we know the maximum time
we do know. Do you know roughly how big these tugboats are? Or sorry, the tugboat?
Yeah.
Oh, tugboat. That one. The idea is like its momentum, because even if you like tried to like ram it, the tugboat is basically it would be like trying to stop a car with a BB gun. So it's just like it has to slowly come into contact, and then start thrusting. Otherwise, you would just end up like Roadrunner, like, or I guess Wile E. Coyote, like smashed across the thing. But for the cargo ship, I have a number up there. I have like a couple of numbers, but do you know how big these things are? It's like they're They're so big. Like it's like large apartment buildings that are on their side, kind of traveling through the ocean. So much mass. So this one, at least for the number that I found, was like mass is 96.5 E6, so like times 10 to the 6 kilograms. So what do you think? How long do we need to apply thrust to bring this thing, or how much thrust do we need to stop this thing?
Are we allowed to say momentum is equal to impulse, just for simplicity's sake?
Can we say that? Is momentum equal to impulse here?
Well, yeah, but I mean the units line up, but
Can I do this and just say like, all right, mv equals F delta T? Maybe. So I saw a nice diagram here. This impulse momentum diagram. So I have an initial momentum, it's traveling to the right with momentum mv. I'm going to add to that the impulse of F delta T. And here I could call it like average F, right? Like for a given amount of time, this is how much average force I need to apply. And then at the very end, the goal is, all right, we want nothing left. We want to actually stop this thing so it's not now moving backwards, that also causing problems. Which is exactly kind of what we started off with just a unit analysis of like, yes, mv equals F delta T, because we're not looking to like change momentum. Well, we're trying to change momentum to 0. So total initial momentum is equal to whatever opposing impulse we had. Cool. So how much force do we need? Good. A lot, yeah. It's a lot. Because we have that 96 million up in the numerator.
What units do you want the force?
I don't know.
I put them in kilonewtons.
Kilonewtons.
but I'll probably put them in meganewtons.
Probably meganewtons would work. Yeah, because we have that 95.6 E6 times, I'll call it 4, all over 60 seconds. So 5.7 E6 newtons.
Meganewtons.
Yeah, time. So it would be 5.7 E3 kilonewtons, 5.7 meganewtons. Yeah, meganewtons. How much thrust can a tugboat actually create? I don't know. A bollard pull of 477 ton force. So 4.8 meganewtons. We're like not too far off. So if we had a full minute, one, like you got to get the tugboat there pretty quickly. So really this is like a half-hour activity to have a tugboat shove on this thing for a full 6. That's a long time to be like max thrust for a tugboat, 60 seconds that way. But it's not impossible, right? We're roughly same order of magnitude because it looks like our max thrust is like 4.8. Like maybe we could get it done in 2 minutes if we had full throttle of tugboat doing full throttle aimed at this cargo ship. Maybe, I don't know. I don't want to be on the tugboat when it's doing this operation, but pencil on paper, it's like it's possible. Kind of a Star Trek sort of operation, giving it max power, sir.
It's also assuming you're pressing on the bow, right?
Yeah, that everything is directly in line, which, I mean, if you've ever been on a boat, keeping things lined up is pretty difficult. Okay, so that one's like a maybe. Maybe we could do that. Maybe. So let's say we'll just build a fender system. So we're gonna have a whole bunch of like rubber tires and just line them up. And the more rubber tires we have, the more like displacement we can use. So basically we're creating something where this boat's coming in, it's gonna hit a spring, and then come to a stop. I guess the problem that somebody else's problem. Somebody else's problem is that now it's going to launch it backwards, but we'll say that there's like damping involved. But rough first order is like how stiff does it need to be to actually bring it to a stop? And then the next problem that we would have to figure out is like when it does launch it back, when the spring actually uncompresses, is it going to send it backwards at the same speed that it was coming in? Probably not. Rubber is a nice, like, hysteretic material. It's an entropy spring. So K, it's like 3E, so it's 3 times 10 to the 6th Newton per meter. How much like delta X do we need? Like how big does our like bumper need to be so that the boat doesn't like crash into the bridge anyway? What do you think? How do you do that one? Okay. Okay. Yep. Yeah. Makes sense. Alright. Yeah, yeah, I do. What are the energy terms that you use? Yep. Yeah. That makes sense. Yeah, so initially you have all kinetic and then all potential. Oh, we can say the boat is 1/2 mv squared. Then the potential energy in terms of 1/2 x squared. So one equals the other. So initially we have that t plus b, but that b is 0, that potential is 0 at the start. So it's just 1 mv squared. Then equals, yeah, t plus b. The other side, so the other side, t is 0, b is, yeah. All right, cool. So it looked like, at least from the first couple of people that I was looking at, remembering like physics mechanics of like energy is conserved in the system. As engineers, I like to always specify that there could be work being done on the system, some kind of like non-conservative forces would be things like friction or damping or I don't know, anything that's like, or even like heat transfer. Like if something is like pulling heat away and taking kinetic energy, turning into heat, that would be like work being done to take things out of your system. And all that's equal to T2 plus V2. So anytime I'm using conservation of energy, I write out all 5 terms. Like I start with something, end with something else, and there's some work being done to get from 1 to 2. Then I can go through and say, to start, let work be 0, because I'm not going to worry about it. Initially, I'm going to let that be 0 too. Like the spring is unstretched, uncompressed to begin with. And then at the end, also kinetic energy should be 0 because I'm hoping to bring this thing to a stop. So now I have a nice 1/2 mv squared equals 1/2 k delta x squared. Nice. And again, conservation of energy is always going to give us velocity position equations. Like it's always some relation between how far did I go and how fast am I moving, which is really useful for this kind of analysis. All right, so what was delta x? How big was this thing? How many meters? 20.3. That one's, it doesn't sound big, but remember, this is, so what I found for this value of K, that's kind of like the stiffness of a tire, like an uninflated tire if you compress it. So it would be 20 meters worth of tires, or roughly about like 20 tires sticking off of the pier. Like, so it's a lot of rubber, and it's got to be stacked high enough that it's actually, like, if every tire is 3 feet, then we need 20 of them sticking off the pier. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I mean, that's a lot of rubber to be like jamming in there. And again, also hoping that it's all solidly packed, that when this thing hits it, it doesn't just like split the rubber and cause it to do something else. Also, can you even get a boat through the middle if you have 20 meters on, I don't know how far apart. Like if you have 20 meters, if this thing is coming out 60 feet this way, 60 feet that way, you might not even be able, you might have reduced the travel lane down to like 10 meters. You're just causing more accidents because your bumpers are designed for the worst case of a giant tanker coming slamming in. Anyway, it's not an easy problem to solve. And yeah, when I was reading articles about this, a lot of the questions were kind of like, why didn't engineers prepare for this? It's like, because like you prepare, like it's like, what do you want? What do you want me to do? Like throw giant rubber fenders around everything so that no one can ever use the waterway underneath? Or do you want tugboats always at the ready that are going to be like there to try to stop these tankers? Like, yeah, it's not an easy problem to solve. But that is our job. Yeah. It's like the offensive line in football. The only time you get some screen time is when you like miss a block and things go wrong. It's like, where were you? It's like, dude, I've been here blocking every play. Miss one, get one person through, cause a safety. Should we call it? We got tests coming up, weekends coming up, and I think we did some great like world-saving calculations already. World will be better as we use our tools for good. Sound good? Cool, thanks.